Hello everyone, welcome to this fresh session on electromagnetic fields. Today we are discussing about the examples on electric field intensity part 2. Today we will discuss few more examples. In this subject, practice related to the examples is very important so that we can answer the question in examination very properly. So let us see this example. In this example, we are given with two charges. One is Q1, that is 5 coulombs, and another one is Q2, that is 1 nanocoulomb. Their location is given in space. It is -1, 1, -3. And Q2 is located at 3, 1, 0 meters respectively. We have to determine electric field intensity Q1 at Q1. So what is the electric field intensity at Q1 is the question. So by default Q1 is the destination. The destination is Q1. So who will be the source? Q2 will be the source. Yes, Q2 is the source. Now if we try to draw them in space, if we have to imagine them, let us consider three axes. So these are our three reference axes. We may also require the negative or minus x, or we may also require minus z. So if we want to identify the point's location in this, so how can we identify? Say for Q1 the points are -1 on x-axis. So this is our x-axis, this one is y, and this one is z. So on x-axis it is -1, so it is going somewhere backside. Then on y-axis it is 1, say somewhere here. So we will attach these points on the floor. So this is point somewhere on the floor, and then it should go on -z downward up to some point -3. So here somewhere there will be the actual location of Q1. Similarly, we can find out where is Q2. Q2 points are given as 3, 1, 0. That means on x-axis it is 1, 2, 3. On y-axis it is 1. So we can attach this somewhere here on horizontal plane. This is the point, and there is no height. So this point itself is Q2. And we have to find out electric field intensity between Q1 and Q2. So this is the R bar, and destination is Q1, so arrow of R bar will be towards Q1. So due to this point Q2, we have to find out electric field intensity on Q1. So let us solve this example. So let us note down the given data. Given data, we have value of Q1 is 5 coulomb, and value of Q2 is given. Q2 value is given as 1 nanocoulomb, so it will be 1 into 10 to the power -9 coulombs. So these are the given values. Available formula, we have electric field intensity is equal to the destination is Q2 divided by 4 pi epsilon naught r square into AR cap. So first let us calculate AR cap. AR cap we can find out by AR cap is equal to R bar divided by mod of R bar. So first we have to calculate then R bar. So what is formula for R bar? R bar equal to the destination points minus source point. So first point is say minus 1, minus 3 for x direction. So it will be ax cap, plus for y component it is 1 minus 1 into ay cap, plus minus 3 minus 0 az cap. So this will be the R bar. So from here R bar will be equal to minus 4 ax cap minus 3 az cap. So this is R bar. So from here we can calculate the mod of R bar. So let us calculate mod of R bar. So let us, what will be the mod of R bar? Mod of R bar will be nothing but the square root of all the 3 direction components. So here we can say R or mod of R bar is nothing but equal to, what is this value? Mod of R bar square root of 4 square, that is 16, plus 3 square, that is 9. So it will 25, that is nothing but 5. So position vector magnitude is 5. So what we have, we can write in the equation of AR cap. AR cap will be equal to R bar divided by mod of R bar. R bar is minus 4ax cap minus 3az cap divided by 5. So after solving this AR cap, this is the value. Now where we have to keep? We have to keep it in the E, that is q by 4 pi epsilon naught r square into AR cap. So let us put the values. So electric field intensity vector, Q is given. What is Q? Q is 1.0 into, for nanocoulomb we'll write 10 to the power minus 9 into 1 upon 4 pi epsilon naught is nothing but 9 into 10 to the power 9 divided by 25 into 5, and the R bar is 4ax cap minus 3az cap. So E bar will be equal to, after solving this, we should get minus 0.288 ax cap minus 0.216 az cap. So this is the solution. So let us move to next example. So next example, it's a it is okay. Now we have given with one line filament, and in line filament it carries uniform charge distribution of rho L. What is rho L here? This is nothing but the line charge density. So we can consider one conductor. So in conductor we have some values given of rho L, and it is having, so we have to find out electric field intensity. We have to find out electric field intensity at some point P2, that is x1, y1 and z1. Some imaginary point is there. We have to find out because of this line charge. So this line charge is applying some electric field intensity at which points? x1, y1, z1. So let us consider that we have some point at origin. For simplicity, that is 0, 0, 0. So let us write it like this. Say point 1 is having some radius 1, which is equal to x1 ax cap plus say y1 ay cap plus z1 az cap, and let P2, which will give R2, is equal to say x2 ax cap plus y2 ay cap plus z2 az cap. So let us consider one as source, one as destination. Say this is destination and this is source. So as usual, we will do source minus destination points to find out R. So this one minus this one. So here we will get x2 minus x1 ax cap, then plus. Next one is y2 minus y1 ay cap plus z2 minus z1 az cap. This is R bar. So since this is R bar, we can find out magnitude of it and AR cap. AR cap is nothing but R bar divided by R. So for the electric field strength at P, to find electric field intensity at P2, what we will get? The formula for electric field intensity, we have to integrate. So in place of Q, what we have rho L. Rho L is equal to say dq by dl. Hence dq will be equal to rho L dl. So in our routine formula, in place of Q, we will write rho L dl. For the whole system, we have to take integration to find out the whole value. Divide by 4 pi epsilon naught r square into AR cap. So then next, we'll take out the constant. So we'll take out constant. Say that is 1 upon 4 pi epsilon naught integration for rho L for given position vector by RQ into dl. So this is the required expression for electric field intensity. So this is the example solution. Now let us move to next example. Now in this example, one diagram is given and we have to find out the electric field intensity. So in this diagram, some data is given. So I will note it down. Say here we have a point P. This is point P. There are these two axes. One axis, this is going R, and on this axis, this is Z, and there is some point A. This point is point A at negative side, and this angle is say alpha 2, and this is origin 0, and differential length is present here. Differential length. This differential length is dl from 0 to L. Then this angle is alpha. This is alpha 1, and this is also R. So this point P have three components. One is resultant, dE, this one is z component dEz, and above is say dE r. So this is radius r, this is r1, this is r2, this is r3. Okay, so this is the setup given, and on z axis the distance will be z. So we have to find out the electric field intensity for this given setup. So we will start with the basic definition of charge density. So how we get that? Any kind of density is directly proportional to the cos of the density. For example, if rho L is the line charge density, it is directly proportional to the charge per length. So from here what we can say? We can say dq is equal to rho L dL. So this is differential charge. Now small r, this r we can get here as, so this r will be square root of r square z minus L square. Now for differential electric field intensity at the point P, so dE at point P will be given by, as it is line charge density, in place of dq we will write rho L dL divided by 4 pi epsilon naught, in bracket we have r square plus z minus L whole square into AR cap. Or we can simplify it, as it is on z axis we can write the differential electric field intensity for z axis is rho L dL divided by 4 pi epsilon naught r square minus z minus L, sorry this will be plus this whole square into cos of alpha. So if we put the limit, we can find out the total Ez. This Ez will be for alpha 2 to alpha 1. That is where we have to find out the electric field intensity. So it will be equal to rho L cos alpha divided by 4 pi epsilon naught r square plus z minus L square into r square plus z minus L whole square divided by r d alpha. So let us substitute tan alpha. So let tan alpha is equal to r by z minus L, or from here we can say z minus L is equal to r cot alpha. So for keeping this we have to change dl also. This dl will be equal to minus r cosec square alpha d alpha equal to minus of r square plus z minus L square by r square into d alpha. So and simplify, on simplification we will get rho L divided by 4 pi epsilon naught r alpha 2 to alpha 1, and here we will get cos alpha d alpha. So if we integrate this cos alpha, this Ez will be equal to rho L divided by 4 pi epsilon naught r sine alpha 1 minus sine alpha 2. So similarly, for differential electric field intensity, say dE r, what we will have rho L dl divided by 4 pi epsilon naught r square plus z minus L whole square into sine alpha. So then ER equal to alpha 2 to alpha 1. So here we'll have this numerator rho L dl sine alpha by 4 pi epsilon naught r square plus z minus L whole square. So here we'll keep the value, that is say r square plus z, I will write down here, this value will be r square plus z minus L whole square by r d alpha. So its solution will be, we'll take out constant rho L by 4 pi epsilon naught r alpha 2 to alpha 1. Inside we'll get sine alpha d alpha. So final expression we will get as ER equal to rho L by 4 pi epsilon naught r cos alpha 2 minus cos alpha 1. So this is the equation, required equation for this question. So now let us move to next example. Say we'll see next example 2.16. So let us see what is given in example 2.16. There is a charge density of rho L equal to 10 picocoulomb per meter. It is uniformly distributed along an infinite line, and we have to determine electric field at point root 2, root 2, 1. So let us solve this. So what is given here? So we have the given field is at root 2, root 2, 1. And what is the value of E here? E will be, this is line charge, infinite line. So we have to use the equation of infinite line here. So it is rho L by 2 pi epsilon naught r into AR cap. So whereas rho L is given, rho L is equal to 10 picocoulomb per meter. So for cylindrical coordinate system, say the r will be given by square root of x square plus y square. As it is infinite line charge going from minus infinity to infinity, for this line we consider the cylindrical coordinate system with components as r, phi, z. So this r is say root x square plus y square. that value will be 2 plus 2 equal to 4. And we also know that 1 upon 4 pi epsilon naught is equal to 9 into 10 to the power 9. Or if we, for line charge, we require 2 pi epsilon naught. So it will be half of it, we have to double it, say 18 into 10 to the power 9. So in our formula of electric field intensity, if we keep these values, E will be equal to 18 into 10 to the power 9 into 10 into 10 to the power 12 divided by 2. The direction is AR cap. So if we solve this, we will get E is equal to 9 into 10 to the power minus 2 into direction of radius. So this is nothing but E is equal to 19 AR cap millivolts per meter. This is the required value of electric field intensity. So with this example we will stop here. In next session we will see more examples on electric field intensity and its cases. Thank you. Have a good day.